The last section in Unit 2 is talking about something called cut. The last section in Unit 2 is talking about a topic called symmetry. And you have probably heard that term used before, but there's different types of symmetry. We have line or reflective symmetry, and we also have rotational symmetry. You are probably most familiar with line symmetry, and what line symmetry is, it's symmetry where a line, let's say a shape can be folded in the two parts match or meet up. Let's say meet up. So what does that actually mean? It means that if I were to take some of these shapes down here, and you can see if I were to take this rectangle and fold it over this line, bring this over here, or vice versa, that the two sides would land on top of each other with nothing extending outside the shape. Well, you might be saying, well, what about, couldn't I do it this way as well? And you're right, you could. You could fold it, we have hamburger and hot dog style, I guess. You could fold it like that, and you would the two parts would land on top of itself. So how many lines of symmetry does this thing have? It actually has, this one right here has 2 lines of symmetry. So we're going to go through these figures to see how many lines of symmetry do they actually have. So this one right here is a regular pentagon where all the sides are congruent. We could fold it right here. I think that one is pretty easy for you to see since we're looking at a shape being folded from left to right. But some of the other ones that are harder to see is this one. Okay. And we have this one. And we have this one. If it's hard for you to see these lines of symmetry on your paper, what you could always do is you could actually rotate your paper to see all these lines of symmetry and see how many do we have. We have, I probably shouldn't have used pink twice. Let's use light blue. Whoops. So we actually have 1, 2, 3, 4, 5 lines of symmetry. 5 lines. Now I'm going to erase these for a second just to show you something. I think we can agree that this one is easy to see. Well, rotate your paper so that this point is vertical right in front of you, kind of where this green point is right now. You rotate your paper so this is there, and you can do the same thing. And you could go on to the other points. Now with this shape right here, we agree that you could do that line and fold it horizontally. But because all the sides are not the same, if we were trying to fold it over this line right here, if we were trying to fold it over this line here, you can see that the two pieces wouldn't line up on top of each other. So because not all the sides of this pentagon here are the same, there is only one line of symmetry here. This triangle, there's actually going to be no lines of symmetry. There's no way that I could, draw a line anywhere and fold this triangle on top of itself. So there's no lines of symmetry here. This is an isosceles trapezoid, and again, I think the obvious one is this one going straight up and down, where I could fold this on top of itself. And then I like to see, okay, what could I do in the corners? Would this be one? Nope, that's not going to work. What about horizontally? Nope, that's not going to work either. So it looks to be that this one also just has one line of symmetry like that pentagon did. Now we have a square. Some people may say this is a diamond, but it's a square. Just, not, it's kind of rotated, and that's why it looks like a diamond. So we have one line of symmetry there. We have one line of symmetry here. But like the rectangle in the first problem, we have a line of symmetry right there. And we have a line of symmetry right here. So this one has 4 lines. And then finally, we have an equilateral triangle where all the sides are equal or congruent, the same measure. We could have that line. Oops. This line. And this line. So there are actually 3 lines of symmetry. And as we have written right here, that the lines of symmetry are also lines of reflection, so we could fold our shape on top of itself over those lines of reflections. Now look at the equilateral triangle. Triangle has 3 sides. An equilateral triangle has 3 lines of symmetry. A square, has all 4 sides that are equal. You could think of that as an equilateral quadrilateral. It has 4 lines of symmetry. When we did our pentagon, a 5-sided shape where all 5 sides were congruent, we had 5 lines of symmetry. We can use it to our advantage later on. Now let's look down here and talk about rotational symmetry. Rotational symmetry is when you rotate a figure less than 360 degrees and the figure less than 180 degrees, and the figure lands now. Rotational symmetry is when you rotate the image and it lands on top of itself. So when you rotate an object or shape less than 180 degrees, and the object lands on itself. Now that 180 degree thing, there is going to be some angles of rotation that are going to be slightly larger than that, but that means there's more than one angle of rotation. And probably the best way to think about that would be a square down here. So if we rotated a square 90 degrees, we could rotate the square another 90 degrees for a total of 180 degrees. We could go another 90 degrees for a total of 270 degrees. And then another 90 degrees would be a full 360 degree turn. So yes, even though we could rotate this square 270 degrees and it would still land on top of itself, the smallest angle is 90, or the multiples of 90 would be our rotational symmetry angle. Now, we can calculate that by using this formula here. From the problem above, we knew that there were 4 lines of symmetry in a square. So if we do 360 divided by 4, that gives us 90 degrees. So that's telling us that the smallest angle of rotation is 90 degrees, and I could keep rotating the square 90 degrees for it to land on itself. So the square has rotational symmetry, rotations of 90 degrees and 180 degrees will land it on itself. Hexagons, a hexagon will have 6 lines of symmetry. So we do 360 divided by 6, and that gives us 60 degrees. So we have 60, 120, and 180 degrees. So I'm counting by 60s. Now you might say, well, why don't you go to 240 and so on? We don't need to go that far. We got 60, 120, 180. Once we hit 180, we can stop. Now look at the kite. The kite has no rotational symmetry because no rotation of 180 degrees or less maps it onto itself. Because you may say, well, there's 2 lines of reflection, the vertical one and horizontal one. So we could do the formula 360. So a kite over here, you may say, well, there's no way I can rotate this and get the shape onto itself unless I go and do a full circle. Well, you can also find that using the formula as well. We have 1 line of reflection here, or 1 line of symmetry. If I do 360 over 1, that is still 360. So there are no rotations of 180 degrees or less that will map the kite or make the kite land on top of itself. So just because something has reflectional symmetry or line symmetry does not mean it will also have rotational symmetry. On the next page, we're going to figure out if shapes have rotational symmetry, and if they do, find that angle measurement. So the first, this weird looking plus sign, that could be a line of symmetry. And this could be a line of symmetry as well. And some people might think, well, what about the corners? Let me draw the corners and see. Well, if we draw those corners, and can you visualize if we folded, would it map onto itself? And the answer would be yes. We have tools that we could use to show that. So the corners are also lines of symmetry. That means your angle is going to be 360 divided by 4, which is 90 degrees. So that is our angle of rotation. Every 90 degrees I rotate that shape, it's going to map or land on itself. This one you can obviously a vertical line, but there's really no other lines of symmetry here. So this one does not have any rotational symmetry because there's only 1 line of symmetry. This heart, the same thing. You have that line there, but that's it. So no. This double arrow, you might say, I agree with that one. And there's also this one. There's no other lines of symmetry. So 360 over 2 is 180 degrees. So this just barely met the requirement for rotational symmetry, where I could rotate this 180 degrees and it would map or land onto itself. And we're going to skip point symmetry. Now identify line symmetry and rotational symmetry of these figures. In this one we can see that we have 1 line there and another line there. So there's 2 lines of symmetry. So then the rotational is 360 over 2 or 180 degrees like that one previously. Then this one has a line of symmetry there. And again, you could go and rotate your paper if this helps you. We can go this way. We can go this way. Or this way. Oh, we don't want to go back here because we already did that. So we have, 1, 2, 3 1, 2, 3, 4 lines of symmetry there, but you can also go this way. So 5, 6, 7, 8. So this shape here actually has 8 lines of symmetry, meaning we're going to do 360 over 8, and that gives us 45 degrees. We could rotate that 45 degrees and get the same shape. This butterfly here only just has 1 line of symmetry, so that means it has 0 degrees of rotation. This football, we're going to pretend that the laces are non-existent. There's 1 line, and there's 2 lines. So that means there's 2 lines, or 360 over 2, which is 180 degrees. What about here? Which of the figures from examples 3 and 4 behave the same rotationally? Well, the arrow in the football and the triangle thing, the inverted triangles, those behave the same rotationally of 180 degrees. And then the triangle, heart, and butterfly all have 1 line of symmetry, but no rotational symmetry. Example number 5, use a description to draw a figure. If not possible, write not possible. A triangle with exactly 2 lines of symmetry. Now we have a triangle up here with 1 line of symmetry, and we have a triangle up here with 3 lines of symmetry. But is it possible to draw a triangle with only or exactly 2 lines of symmetry? It is not going to be possible, because if you could have 2 lines of symmetry with a triangle, then you could have a third. Not possible. A regular hexagon with no rotational symmetry. Well, we just found out that a regular hexagon has 60-degree rotational symmetry, so this is not possible. A trapezoid with exactly 1 line of symmetry. We did that at the very beginning. A trapezoid that looked like this had 1 line of symmetry going down, straight down. And then a quadrilateral with exactly 2 lines of symmetry, we did that too, like a rectangle at the very beginning. We could have this, or we could have this. So that would be our quadrilateral with exactly 2 lines of symmetry. A rectangle would work. So that's it with symmetry. Again, it's something that I'm sure you've seen before, but now we're actually getting to the math part of it. So hopefully you understood this video. Thank you for watching, and make sure to like and subscribe.